Can I start?
Okay, so hello everybody. Today it's a great pleasure to have Emanuele Berti from Johns Hopkins University. He will tell us about nonlinearities, gray body factors, and resonances in black hole ringdown. Please, Emanuele.
Thanks for the invitation. I have many things to say, and I have 50 minutes, right? More or less.
Yeah, but it's flexible. You can go a bit over. It's not a problem.
Okay. Let's see how far we get, and when we're close to the end, maybe tell
I
me
mean,
that I'm
including the questions, it's an hour, and usually we go over time, so it's not. Yeah.
Sounds good. So I will start. Let me explain the structure of the talk. First of all, I should even before I start, I should say that almost everything I'm going to talk about is not really my work, but the work of the many students and postdocs who are here at Johns Hopkins. And the composition of the group has been changing a lot lately. All of the people that you see marked in blue are postdocs or graduate students who are finishing or have finished recently. For example, Jay Wadekar is now a faculty at UT Austin. Uh, Mesut will start as a Simons collaboration postdoc in Montana. Vion Kapil is going to work for Meta. Kostas Kritos won a Hubble Fellowship. Luca Reali will join the AEI with John Gare and will also be involved in the Simons collaboration. Nick Spinney got a postdoc working with David Nichols and Ken Tiaghi at the University of Virginia. Mark Chung is now in Princeton. Sipeng Wang is in Barcelona working on numerical relativity. So I am left only with two students, but three new students are going to come in the fall. So the composition is changing. Many of these people are working on different aspects of ringdown. Also, there are new things that are coming out next week, but we are literally finishing the paper now, and I didn't have time to add any slides on that. But I can tell you what we've been doing, and you will see it on the archive next week. There are many things going on. So let me explain the structure of the talk, first of all. I will start with a little historical introduction that many of you have seen if you have seen me give talks before. And I don't want to spend too much time on this, but for the people who are not working on black hole perturbation theory or gravitational wave physics. If you have any questions, that's your time to ask questions because I'm going to give a general introduction on why we're doing what we're doing. The meat of the talk is going to be what's in the title. That is, I will talk about what has been making, in my opinion, this field particularly exciting in the last couple of years, namely the study of nonlinearities in binary black hole mergers, the study of the excitation of different quasinormal modes, better understanding of the Green's function, and um, also a better understanding of the role of the so-called gray body factors, both in terms of theory and in terms of what we can do with them with LIGO observations. And last but not least, spectral instabilities, the role of resonances between different quasi-normal modes, and how we can use all of this machinery to test theories beyond general relativity. I'm pretty sure I will run out of time at some point, so let's see how far I get, but I'll try to squeeze all of these topics in. So let me start with an introduction of what black hole spectroscopy is, how it went from a purely theoretical topic to something that is of relevance to experiments right now. The whole story begins many years ago, 110 years ago, more or less, 111, with the discovery of the Schwarzschild metric. You all know that for a very long time it was thought that this was just a Schwarzschild singularity with no physical relevance. There are two apparent singularities in the metric. One is a real curvature singularity, the other one is a coordinate singularity. But initially, the study of the properties and stability of the Schwarzschild metric was motivated by understanding whether, number one, it had anything to do with physics at all. So there was the initial work by Oppenheimer and Snyder that said that if you assume non-interacting matter, namely dust, matter with density but no pressure and spherical symmetry, then this metric is actually the outcome of gravitational collapse. And this was challenged by the Russian school, and there was the whole story of the BLK singularities, where they said that the outcome of collapse should not generically be a singularity because, in the absence of spherical symmetry, there are many other more interesting possibilities. Then John Wheeler and his group in the 1960s, 1950s and 1960s tried to understand better whether nuclear forces can halt the collapse. And this led to a lot of work both on the nuclear physics side and on the mathematical physics side that led famously to the Penrose-Hawkins singularity theorems that proved that singularities are in fact the generic outcome of collapse under very mild assumptions on matter, on the properties of matter. So at that point, that's where our story begins. Once people understood that the Schwarzschild solution can be the outcome of gravitational collapse and the Kerr solution more in general, the next obvious question to understand whether these metrics have anything to do with physics was to understand whether black holes are stable. And this led to the development of black hole perturbation theory, the understanding of what quasinormal modes are, and ultimately what we're doing now, black hole spectroscopy. So in the terminology of Kip Thorne, the golden age of black hole physics was the 1960s, early 1970s, when there were developments both on the theoretical side and on the observational side. On the theoretical side, Roy Kerr discovered famously the solution that describes rotating black holes. So the question of what happens to a spinning star when it collapses was at least partially answered because there are solutions that describe rotating black holes. And then on the observational side, there were the first observations of quasars by Martin Schmidt and of what we now understand are stellar mass black holes by Giacconi and Gursky, who were studying X-ray sources and discovered Cygnus X1, which famously had a mass that was incompatible with being a neutron star. So this led to a lot of theoretical work to understand the structure and stability of black holes, and in particular, Sol Tsiolkovsky came up with an equation that describes perturbations around a rotating black hole. And this led to all of the flurry of activities that happened in the following 50 years or so to study the structure and stability of rotating black holes. Now, there was a workshop that we organized in 2024 where we tried to bring together a large community and discuss all of the latest development on black hole oscillations and stability. This led to a giant review that we submitted to classical and quantum gravity. We finally got the proofs. It should be published within the next week or two as soon as we respond to the proofs. And if you are curious and want to go into much more detail than what I can give you in 1 hour, you can look at this review. If instead you want a much gentler introduction, there is a Physics Today article that I co-authored with my former student, Mark, who is now at Princeton, and Sophia, who is still here, on how black hole spectroscopy can put general relativity to the test. And if you want a non-technical introduction to what I'm going to say today, this is a good place to start. So let me get a little more technical now. What's the story? In the 1950s and then in the 1970s, John Wheeler and Tullio Regge and then Franz Zerilli understood that if you consider, just to start simple, a background Schwarzschild black hole, and you write down the perturbation equations that describe the perturbations induced by scalar electromagnetic or gravitational fields, you can separate out the angular dependence by using appropriate angular bases. They're going to be ordinary spherical harmonics for scalar fields, going to be vector harmonics for vector fields, and tensor harmonics for gravitational fields. And when you do that and you separate the time dependence by using Fourier analysis, you discover that all of these classes of perturbations satisfy a wave equation. that goes under the name of the Regge-Wheeler equation for perturbations about parity, or the Zerilli equation for perturbations of even parity. And S equals 0 corresponds to scalar perturbations here. S equal 1 corresponds to vector or electromagnetic perturbations. S equal 2 corresponds to gravitational perturbations in the odd sector. And in the even sector, you have a potential that apparently looks very different. One of the big surprises, and this is the subject of the paper that I will not discuss today, is that the even and the odd sectors are related by a remarkable property, which is isospectrality, and that means that the eigenvalues that I will describe later on of both even and odd perturbations are exactly the same in general relativity, as was demonstrated by Chandrasekhar. Um, all of this work was motivated by the fact that in the late 60s, Joe Weber claimed detection of gravitational waves, as you probably know. And so, in particular, Zerilli's thesis starts off by saying that he was trying to solve the full problem of two black holes merging and producing gravitational radiation, because Joe Weber had detected events that may well prove to be pulses of gravitational radiation. And Dyson at the time had proposed, probably only half seriously, that those events may be the results of encounters between stars and black holes. And of course, the world has changed a lot since then, but the original motivation was exactly the same reason why we are now so interested in this. And what Vishu found when he tried to understand what happens when you scatter radiation on black holes is that there is a very general structure where this plot is right to left, but it should really be read left to right. Initially, you have a transient phase where the amplitude of the radiation that is emitted when you scatter a Gaussian wave packet increases. Then there is a peak, and then there is a damped oscillatory behavior that over time we started calling the ringdown, because it looks very much like the sound that would be emitted when you strike a bell using a hammer. And what Vishu found remarkably in 1970 was that the frequencies and the damping times of the oscillation modes in this damped sinusoidal phase do not depend on the details of what strikes the bell. So you can use different sets of initial data and you will find that the frequencies and damping times are always the same. What does depend on the details of the perturbation is the amplitude of these oscillations. And this is one of the very interesting topics that we are still trying to understand today. Then there was a lot of work that confirmed that, in fact, these damped oscillations were a general property of black hole perturbations. In particular, in the early 70s, there were pioneering studies by the groups at Princeton and Caltech, Davis, Ruffini, Press, and Price, where people took a particle, dumped the particle along the symmetry axis of a Schwarzschild black hole, and they studied the radiation that is produced in this process in the frequency domain. And what they found was that the energy emitted per unit frequency increases up to a peak where the frequency of this peak corresponds almost exactly to the frequency of the quasinormal modes of the black hole, the proper oscillation modes of the black hole, and then the radiation drops exponentially. And now we understand that this is related to the properties of the potential barrier of that I was showing you before in a way that I will make more precise in a minute. Also, as I said before, in the 1970s, Tchaikovsky generalized the formalism by Zerilli and Regge-Wheeler to the rotating case, which led to lots of interesting developments. Already in the late 70s, two things happened that are very important to the story I'm telling you today. One is that Chandrasekhar and Detweiler, and then Detweiler alone, carried out calculations of the full oscillation spectrum of black holes, both in the non-rotating case and in the rotating case. At the end of the calculation of the Kerr spectrum in 1979, Detweiler says that one day after the advent of gravitational wave astronomy, the observation of the resonant frequencies of the black holes might finally provide direct evidence of black holes with the same certainty as, say, the 21 centimeter line identifies interstellar hydrogen. That's exactly the black hole spectroscopy idea that we're discussing today. Also, in the late 70s, people were trying to understand whether these modes could be excited in processes that lead to the formation of black holes. For example, Cunningham, Price, and Moncrief studied the gravitational waves that are emitted when a star collapses to a black hole. And the plot that you see here was their attempt to extract what we now call the ringdown radiation. And what they found is that there was a damped exponential behavior. When they fitted that behavior with a damped exponential, then they found the curve that you see down here, which displays another damped exponential behavior. So they were already observing that not only the fundamental mode, but also overtones are excited in generic processes that lead to the formation of black holes. In fact, someone that you know very well, Zvi Piran, together with Richard Stark, in the mid-80s, carried out a study that was completely ahead of its time, 20 or so years ahead of what everybody else was doing in the late 90s, early 2000s, where they studied rotating collapse to black holes. And once again, the story was the same. They observed both the fundamental mode and the overtone as being present in the waveforms that they computed. All of this to say that this story that we're exploring now of the excitation of different modes is not really new, something that we knew in the 70s and 80s. So let me explain what all of this spectrum is and how it comes about. The general structure of the potentials that Reggie Wheeler, Zerilli, and then Tucholsky found is always the same. The potential has the properties that it goes to zero when R goes to 2m in the Schwarzschild case, or R star goes to minus infinity if you use the so-called tortoise coordinate that expands the radial profile to go all the way from minus infinity to plus infinity. So the potential goes to zero at the horizon. It also goes to zero at infinity unless you consider massive field perturbations, which I will not really discuss much at all today. And so what you want to do, this is the key insight in the years that led from the Regge-Wheeler equation to the thesis by Vishu, is that you want to impose the appropriate boundary conditions. For that, we had, what was needed was the development of the Kruskal diagram and so on. But basically, the idea is that you want to impose purely ingoing radiation at the horizon and purely outgoing radiation at infinity if you want to study the free oscillation modes of a black hole. Because in general, at infinity, you can have a combination of waves going in and out. But if you want to study the free oscillations of a black hole, you want to impose that the amplitude of the incoming waves is equal to zero. So imposing these two boundary conditions on the wave equation leads to an eigenvalue problem for the frequency omega. This is the problem that Chandrasekhar and Detweiler solved first. And they realized that the spectrum that you get is a discrete spectrum with an infinite number of frequencies for any angular number Lm. And these frequencies are called the overtones. The spectrum looks pretty much like this, for those of you who don't work in this area. So if I take a non-rotating black hole, then the spectrum of the dominant gravitational perturbations will correspond to L equal 2 because gravitational radiation is quadrupolar. You will have a mode that has a very small imaginary part. We call that the fundamental oscillation mode. And then you will have several overtones with ever-increasing imaginary part. The spectrum has a very interesting structure that I will not describe. But the key idea is that the modes with the lowest imaginary part should typically dominate the waveform that we observe because they last longer. Now, when you go from the non-rotating case on the left to the rotating case on the right, what happens is that each of these modes, for example, the fundamental mode that you see down here, gets split pretty much like in quantum mechanics. You have a Zeeman splitting when you put your hydrogen atom in an electric or magnetic field. And the splitting will depend on the magnitude of the perturbation. In the case of atomic physics, it would depend on the magnitude of the electric field. In this case, it's going to depend on the magnitude of the spin of the black hole. So you're going to get a family of modes with different azimuthal numbers that go from -m to m, and how far each of the LM modes is going to be from the non-rotating value will depend on the spin of the rotating black hole. Now, the reason why Detweiler was claiming that we can use this to do spectroscopy is that in general relativity, all of these zoo of frequencies with different L, M, and N depend only on the mass and the spin. So we now know from numerical relativity simulations that the mode with L equal M equal 2 is the dominant one. Imagine that I observe a waveform with LIGO. I see a damped exponential. I try to fit that damped exponential and I get out a frequency and a damping time. Then all of the other modes are uniquely determined by the mass and the spin of the remnant black hole that I have observed. And if I measure any other frequency, I have a test of general relativity. If the signal is loud enough that I can measure many frequencies, then I'm going to have multiple tests of general relativity that I can combine in the same way that people who do binary pulsar observations carry out tests of general relativity by combining different observables. So this is the key idea. Now, the structure of the spectrum is very interesting because there are two things that happen, and I want you to keep them in mind for what I will say later. So one is that the mode with L equal M equal 2, and in general, almost all of the modes with L equal M have the property that if I take the spin and I go to the extremal limit, the limit where the spin goes to 1, then the imaginary part of those frequencies goes to 0, which signals a potential marginal instability of black holes when you go to the extremal limit. The second very curious thing that happens and that I will describe later is that not all of the modes do this. So you see here that if you take, so this is the fundamental mode, n equals 0, then you have 1, 2, 3, 4. You see that the fourth mode starts doing something strange over here. The fifth mode doesn't want to go to that quasi-stable limit at all, but it turns around. And you see that also the next mode, the one with n equals 6, seems to be doing something strange here. Now, this is related to something that is well known in quantum mechanics and non-Hermitian physics in general, which is the phenomenon of avoided crossings. And it has been understood in much more detail in the last few years. And it can lead to very interesting consequences that you will see in some papers that we are preparing for Kerr-de-Sitter black holes and many other things that I will not have time to describe today. But so there are very curious phenomena that happen. Another thing that I want you to keep in mind for what I will say later is that it's been understood already from the 90s that if I take, let me go back, the potential that you see here, and I replace it by, say, a discretized version of the potential, where instead of using the full functional form that you see here, I replace it by many discrete steps, then the spectrum is going to look completely different. So the spectrum itself is unstable under small perturbations. For example, it's going to look completely different if I discretize the potential. However, this doesn't really affect what I observe in the time domain to leading order in some sense. That, again, I will try to make more precise later. Okay, so I told you that the key idea is we can make these tests as long as the modes are excited and observable. So this led to a lot of activity already in the 80s and 90s to understand which modes are excited. The key paper here is a work by Lever in 1986, where he understood the following property, that if you consider the Green's function, which is basically the kernel of the integral that you have to solve to integrate the differential equation in the frequency domain, then you realize that The Green's function contains three main components. One is related to an integral along a large semicircle, and that corresponds to what we call the prompt response. Basically, if you take the particle and you dump it into the black hole, you will have a signal that is emitted by the particle itself and corresponds to a large frequency perturbation. Then there's going to be two more components. One is traditionally associated to the fact that the differential equation has a singularity at omega equals 0. And so you need to deform the contour in the way that you see here. That contribution, the one that comes from the integral along, around the singularity, gives you the so-called tail term. It gives you a power law dependence in time at late times. And then there is a third contribution that corresponds to the poles inside this integration contour. That is what is called the quasinormal modes. Now, the residue at the poles is something called the excitation factor or excitation coefficient. And that is really what you want to know if you want to understand which modes are excited by any physical process. In fact, Lever already in the 1986 paper computed these excitation factors and excitation coefficients, the residues at the poles, and he compared his predictions with numerical waveforms that have been computed by the group, by Price and others. And what you see here is that when you take the analytical calculation of the excitation coefficients, there is no fitting involved here. You just compute more and more of these excitation factors and you compare them with the numerical waveforms for a point particle, you get better and better agreement at earlier and earlier times. Good. Okay. Then, later on, we repeated this calculation for rotating black holes, and we found the same result, basically, that as you include more and more overtones, you get better and better agreement when you take a particle and you dump it along the z-axis of a rotating black hole. We did that case because it was by far the simplest. I'm telling you all of this story because there have been some interesting developments that I think some of you there are interested about, and there was recent work by Yoshita, Motohashi, our own group, and I will tell you about this later on. Then two more things happened. One is that in the early 2000s, 2005, Franz Pretorius finally managed to evolve binary black holes to merger, and people started fitting quasi-normal mode superpositions to numerical simulations, and they found the same behavior. As you fit more and more modes, you get better and better agreement close to the peak. And then we did the same for unequal mass simulations. We extracted the waveform amplitudes and so on in a paper in 2007. Then people started developing fancier and fancier Bayesian techniques to do mode inference from actual observed waveforms. And then, of course, 10 years later, there was the first detection, and this is why we're here talking and why the gravitational physics community has grown so much. Immediately after this first detection, if you just look at these waveforms, you will see that they're very noisy after the peak. So initially, the LIGO collaboration was very cautious about whether we were doing ringdown tests, and they only claimed that the waveform was broadly consistent with the predictions of general relativity, but they didn't go very far in making additional claims because the signal-to-noise ratio in the ringdown for this first event was about 7. So you cannot really measure anything with such a low signal-to-noise ratio. But then there were other claims that you could actually extend the waveform by just fitting all the way to the peak. In particular, there was this paper by Gisler et al. Caltech that said, if you just compute the mismatch between a superposition of quasi-normal modes and the full numerical waveform, you can go all the way to the peak. And it's true that if you include more overtones, you can do better, but then there were claims that you could use the quasi-normal mode superposition at the peak to detect additional modes, and I think that these claims were not justified given the signal-to-noise ratio that we had at the time. So I would say that by now, the community agrees that we were crying wolf, that those early claims were probably exaggerated. But as you know, just 1 year ago, there was an event with much larger signal-to-noise ratio where the evidence for these additional modes is much more convincing. What came out of that controversy, besides a lot of stress and me aging prematurely, is that we now have a much better understanding of nonlinearities in the merger and ringdown. And let me explain why. So, the key source of the controversy was the idea that if you want to fit a damped exponential and extract a quasi-normal modes, what you get will depend on the starting time of the fit. So as you can see here, in general, I want to extract an amplitude and a phase, and I can or cannot assume that the frequencies depend on the mass and the spin in the way that is predicted by general relativity. So there are two classes of tests that you can make. In one, you can say, I don't know anything about my signal. I just want to go out and measure the frequency and the damping time. In another class of tests, you can say, I know all of the spectrum because I know general relativity and I know that deviations from general relativity are going to be small. So I assume that given a certain mass and the spin, all of the frequencies are known, and I only want to measure the amplitudes and the phases. You are free to do it any way you want, but what you get out of these fits will depend on the starting time, as you can see here. So what I expect is that if I go to larger and larger starting times, I'm going to get something that is more and more consistent with a Kerr black hole, because perturbation theory would be a good approximation. Now, what we realized, and not just us, also other people had pointed this out before, for example, this paper by Sweta, is that if you try to extract the amplitudes using a different number of overtones, then you get an answer that depends on the number of overtones that you extract. If your exponentials are really a good fit, the amplitudes of the modes should be constant, and it turns out that in general they are not. For example, if you fit with a single mode, your amplitude is only going to be constant about 10 or 12 m after the peak. If you fit with two modes, the amplitude of the fundamental mode will be constant at all times, but that's because now it's the first exponential that is eating up all of the nonlinearities, and so on and so forth. So what was understood here is that you have to be very careful and understand what model you are using before you make claims that something is happening at times t close to zero, close to the peak of the radiation.
May I ask a question here?
Sure.
So, is this analysis, does it take into account any noise in the data, any type of cleaning of the data, or is it just a theoretical study of functions?
This was just a theoretical study on numerical relativity waveforms. So we minimize the noise and there is no data analysis involved. But in this slide, what you see is the result of trying to fit different modes, in particular here, two modes to the actual data. And what we pointed out in some papers, Disco Testa et al., is that the initial analysis by Easy and others that found a non-zero amplitude for the overtone suffered from two problems. One is that the fit was done too close to the peak, and the second is that the location of the peak itself is very uncertain because it's determined by fitting a numerical relativity waveform. And so you see that there is an inherent uncertainty in the peak itself that you should take into account when you perform your data analysis. So the bottom line is that different groups that you see listed here found different results for the inference of the first overtone in the original event. But by now we have much more evidence for the existence of an overtone from the 25 or 114 event that we'll discuss later on. Okay, does this answer your question? So,
Actually, I was actually interested in whether, since you followed the peak for quite a long time, the stability of the data, some noise, some nonlinear noise, does it affect in any way the answers, in
it
addition to
does.
the factors
It,
that you...
yes, it does. And if you look at this Baibab et al. Paper, we studied it in a lot of detail. We have many appendices in which we did all sorts of experiments with different levels of noise, including or non-including tails and so on and so forth. I could spend a lot of time on this, but please let me move on and then we can discuss it separately. But the bottom line is that the modes are stable in a finite region about, I would say, 5 to 10 m after the peak. Okay?
Thanks.
So the other thing that came out of this analysis is that what's going on close to the peak? This is a problem that actually motivated all of numerical relativity. People were trying to understand what nonlinear effects happen when two black holes merge. And initially, they couldn't solve the Einstein equation, so they developed second-order perturbation theory in various attempts. For example, some of the early work was by Gleiser et al., and then by Campanelli and Lusto for the Kerr case. After the 2005 breakthrough, several other people actually said, well, we should also see nonlinear modes. And the key idea is that if you push perturbation theory to second order, what you can do is very similar to what you do when you study the anharmonic oscillator in say, even classical physics. Basically, you say that the differential operator acting on the second order perturbation will be the same as in linear perturbation theory, but with a source now that is proportional to the square of the linear perturbations. So there should be oscillation modes that have an amplitude given by the product of the amplitudes of the modes at linear order, and a phase that is given by the sum of the phases. This has been studied by a lot of people in the last few years, and numerically, for example, in these head-on simulations that we did with Mark Chung and others, where we took two black holes and we smashed them together at speeds close to the speed of light. And by tuning the central mass energy of the collision, we can produce stronger and stronger nonlinearities in the ringdown. We were interested in doing this because the amount of nonlinearity that is present when you do the more relevant astrophysical simulations of quasi-circular black holes is very similar among different simulations. Well, in this way, we had a knob that we could tune to produce more and more nonlinear ringdowns. So what you see here is that you get waveforms like this, and you can fit them. Let me move forward. You can fit them to check that prediction that I told you about one moment ago, namely that the amplitude of the nonlinear modes should be proportional to the product of the amplitudes of the linear modes that are driving them. That's exactly what we tried to do in that paper with Mark. And we found that indeed the amplitude of putative quadratic modes in the 4-4 multiple is what you would expect. So there are nonlinear modes in the simulations. And then, of course, these open the gates to a whole set of activities trying to extract the amplitudes of these nonlinear modes. I will not say much about this, but there are by now fitting tools that you can download. For example, the one developed by my student Mark, who is now at Princeton. And from these fits, you can extract the amplitudes of both the linear and the nonlinear modes, and you can try to fit them to the parameters of the progenitor black holes that form a given remnant. So there is a whole phenomenology of doing these things. I can go into excruciating detail into this, but I will not. What is interesting is that some of the predictions that you find from these fits on numerical relativity simulations seem to be in good agreement with both linear perturbation theory, as you see here, with some level of disagreement that I will not discuss, and also with predictions from nonlinear perturbation theory. There is a lot of work on this, but I'm running out of time, so I will skip some slides and I will go to my next topic. Okay? If you have questions, I can go back to this. For example, now there are claims that you can still extract many overtones from numerical relativity simulations. However, even Gisler et al. Now say that if you want to extract all of these overtones, you have to be careful and include all sorts of nonlinear modes, and you have to perform piecewise fits, and there's a lot of technicalities here, but we all agree at this point that stable amplitudes are only possible some 8m or maybe 5m. We can argue about this after the peak. What is interesting and what came out of all of this is that these nonlinear quasi-normal modes are potentially observable. So with Sophia, my student here, we try to understand whether next generation detectors like Cosmic Explorer or the Einstein telescope could have observable quasi-normal modes, nonlinear quasi-normal modes. And we found, I will just give you the punchline without going into the details of the astrophysics and the modeling, that next generation detectors on the ground could detect of order of a few events in which you have observable quadratic quasi-normal modes. It could even be better than this if you do clever data analysis, which we didn't do in that initial paper. And for LISA, the prospects are even more promising because LISA will typically detect mergers of massive black holes with very, very high signal-to-noise ratios. And then as long as your modeling is under control, you should be able to detect, depending on what the universe gives you, possibly tens of events in which you can observe these nonlinear quasi-normal modes. Okay. There are rates in that paper that you can read, but I'll move on to my next topic. Like I said, much of the controversy was now put to rest by 250114, but I have to say that some of the LIGO claims in the original paper are maybe a little shaky, and Mark, without me, is now working on more careful data analysis of this event, and just keep an eye out on the archive in the next weeks or months because he's doing a more careful reanalysis of the claims in the original paper. I will also mention only briefly that we are now developing much more careful models of the ringdown where we try to include a certain number of linear and nonlinear modes. And there are instruments in data analysis that you can use to understand how many modes are needed. For example, in this paper with Francesco Crescimbeni, we try to understand how different ringdown models and effective one-body models perform relative to each other by computing the mismatches between all of these different models and the different multiples of the SXS waveforms. And again, I can go into detail, but I will not. I will only do it if you ask me questions at the end. Last but not least, there have been claims that 250114 already contains nonlinear modes that are detectable. Let me say that I tend to be very careful. We have heard this story before, so there are papers out there that make these claims, but I think we need to be careful and not cry wolf too early. Okay, so let me go to the second part of the story that I wanted to tell you, which is in the last, I would say, couple of years, there has been a lot of exciting, sorry for the terrible pun, work on better understanding the excitation of the modes and the Green's function and the greybody factors. So one thing that we tried to do, taking baby steps, is we went back to the original, the original works from the 80s, where people tried to compute analytically the excitation factors. And I told you that Cleaver did it only for the very simple case where you take a particle and you dump it radially into a Schwarzschild black hole. There has been a lot of interesting work by Kuchler, Honnet, Jeffrey Compere, and others, where they try to do these calculations within an effective one-body self-force framework. I saw that some of the people from that community are here today. We can discuss those papers. They are super interesting. What we try to do is what I know best, which is we took particles that fall from the innermost stable circular orbit into a rotating black hole on the equatorial plane, but the formalism that we developed is completely general. In fact, we are generalizing now to the off-equatorial case. And we try to extract analytically the excitation factors and the excitation coefficients, that is, the C's that appear here, using perturbation theory. And I think that what we found is very interesting and maybe slightly unexpected. We found that the amplitude of the fundamental mode decays as you go to the extremal limit, but the amplitude of the overtones do not. In fact, if you zoom in close to the extremal limit, you see that the amplitude of the first overtone and of the second overtone tend to increase more and more. And I was showing this result at a meeting of the Simons collaboration that we had recently in Chicago, and Shahar was there. And he told me, you should really read my paper from 2014, which since then I did. And so there are some very interesting analytical predictions in the paper by Shahar and others, which are based on this near neck approximation. So the two calculations are, they make different assumptions, let me say. So they should not be perfectly compatible. In fact, from preliminary results, we find that they are not perfectly compatible, but the general trend that Shahar and others predict here seems to be in broad agreement with what we find, namely that the amplitudes of the overtones should become more and more excited as you go to the extremal limit as the overtone number increases. And I think this has very interesting possible implications for gravitational turbulence and many other stories that people have been exploring recently, the Aretakis instabilities and so on and so forth. I will not go into all of this. Once again, we can discuss at the end. A second story that I want to at least mention here is the direct wave story. So this is something that has been studied for a while, starting from an interesting paper by Mino and Brink and a follow-up paper by Aaron Zimmerman and Yanbei Chen. And the story goes like this. They studied near-horizon perturbations, and they found that in principle there should be an oscillation mode of black holes that is associated to near-horizon perturbations, which has real part proportional to the frequency, angular frequency of the horizon, and imaginary part that is proportional to the surface gravity. This mode initially was considered interesting, but not observationally interesting, because the paper by Zimmerman and Chen pointed out that if you take a particle and you dump it into the black hole, then two things should happen as the particle falls in. Your horizon mode is going to be excited as the particle gets closer and closer to the horizon, but it should also get more and more redshifted as the particle gets close to the horizon. And the second effect that makes it harder and harder to observe is the fact that the radiation is produced as your black hole, as your particle falls into the black hole, will have to go through the light ring, and so it will be suppressed by basically the gray body factor of the black hole, which is the transmittivity of any perturbation as it is emitted from below the light ring, and it has to go through the potential barrier and be detected at infinity. However, there was a paper recently by Yoshita and others who claimed that, in fact, when you filter out a certain number of overtones, this direct wave, as they call it, should be present in the data. And I have to say that I'm a little, as by now you should see a trend here, I tend to be very skeptical, and we are trying to check these claims with Shizhen Mao, who was one of the co-authors of the original paper. And I think that what you actually see depends on how careful you are at extracting the overtones. I will leave it at that. Once again, we're working on it, and we will have something to report within the next few weeks or months. Okay. A second very interesting thing that happened, at least interesting to me, is that the old story by Lever has now been somehow retold in a different language. There's been very interesting work by Kuntz, Arnaudo, and others, where they studied the behavior of the Green's function not in asymptotically flat spacetimes, but in Kerr de Sitter. Actually, I take it back, in Schwarzschild de Sitter. We are now working to generalize this to the rotating case. But what they found is very interesting. They found that if you consider perturbations not in asymptotically flat spacetime, but in Schwarzschild de Sitter, then you can replace the branch cut by a sum of pure imaginary modes, which are known from other fields of physics as the Matsubara modes. And basically, they understood that you can decompose the full Green's function in Schwarzschild-Sitter as a sum of the ordinary quasi-normal modes, indicated schematically here in black, and the Matsubara modes. And when you do so, what people traditionally called the prompt response can actually be written as a sum over the Matsubara modes with certain excitation amplitudes. I find this extremely interesting because it tells you that you can compute everything in Kerr or Schwarzschild-Sitter, including the excitation of the modes. Then you can take the amplitude of the magnitude of the cosmological constant going to zero, and you can recover the full waveform using only a sum over quasi-normal modes plus Matsubara modes. And I think that this has potentially very interesting implications also for phenomenology that we're now investigating. Last part of the story on the Green's function that I want to tell you is that there has been a lot of work trying to model initially this work by Okabayashi and Oshita and previous work by Oshita. They were trying to understand the ring down for particles falling into rotating black holes, in particular close to the extremal limit. And what they observed in some of these papers by Naritaka and others is that the amplitude of the radiation that you observe seems to be proportional to a quantity that is well known to black hole perturbation theory practitioners. This quantity is called the reflectivity R, which is related to something else called the greybody factor. Basically, like I said before, the reflectivity tells you how much of the radiation is reflected or transmitted through the peak of the potential. And what Oshita found in some early experiments that he did was that the amplitude seems to be proportional to the square root of the reflectivity, which, when you think about it for a minute, is very reasonable. What we did in a couple of papers led by Romeo Felice Rosato and Sofia and others was to extend this model to the whole SXS catalog. And we found that a minimal modification of the original idea when you include a power law of the frequency is sufficient to reproduce the amplitude of the waveform in the frequency domain with extremely small mismatches. So it's possible to model the frequency domain amplitude of the ring down to very, very good accuracy, say 1 part in 10 to the 4 or so, by simply taking the Fourier transform of the numerical waveforms and using a phenomenological fit in which these parameters A and P depend on the parameters of the progenitor in a way that can be computed. Very nice. What we did more recently was we said, okay, what about yes?
Can I ask a question? When you do the Fourier transform, you do it only on the ring down part?
No.
On
So
the whole thing?
Yeah, we take the Fourier transform of the full in spiral merger ring down waveform, and then we look at the amplitude in this first paper that you see here, and we say, if you compute the reflectivity in black hole perturbation theory, and then you just fit every waveform in the catalog, all thousands of waveforms, by a model in which you take the reflectivity and you multiply by an amplitude and you divide by a power of the frequency. This gives you a near perfect match with the amplitudes of all of the simulations, with parameters A and P, the amplitude and the power law, that depend deterministically on the parameters of the progenitor. Okay? And this fit, actually, to answer your question, depends very mildly on where we started, unlike time domain fits. This is the key idea. So then we said, okay, let's try to fit also the phase. And we found that the mismatches are incredibly small for both the amplitude and the phase. So we proposed a new test. The new test goes like this. The reflectivity itself depends only on the spin of the remnant. So I can now take this gray body factor model and fit it to the data, to the frequency domain version of the data to extract the mass and the spin. And then I can use the gray body factor fit to compare, for example, with what I get from the traditional ringdown analysis. And you see that the traditional ringdown analysis is affected by the starting time and the number of overtones that you include. You get the vertical line is what you will get from a full IMR or from an injection. The red is what you get if you include only the fundamental mode and you start very late. The green is what you get if you do the LVK analysis closer to the peak, but with two modes. And you see that they are broadly consistent with what you would expect from IMR, but they depend on the details of how many modes you include, where you start, and all of the caveats that I was making before. With this gray body factor thing, you get smack on the right value of the spin that you will get from the full IMR, and you are very insensitive to the initial frequency at which you fit the gray body factor model, which I find remarkable. We were very excited with this result. Okay. How much time do I have? Zero.
You can take a few more minutes.
Okay. I only want to tell you very few things about the spectral instabilities. Let me skip the story of the potential with a bump thing. You can make quasi-normal modes unstable by adding just a small bump, and this is very interesting. And the thing that I want to tell you is that I am becoming more and more interested in the resonant excitation of different modes because of the story that I was telling you before, that in GR, some modes exhibit this avoided crossing phenomenon. Now, what was understood in these nice papers by Ayato Motohashi, I went to visit Ayato for about a month in Japan to talk about these things, is that when you go close to the avoided crossing, the amplitudes of the modes get resonantly excited. This was understood already in quantum mechanics, non-relativistic quantum mechanics. It's a well-known phenomenon that it just took and applied to black hole perturbation theory. And it turns out that the modes get excited along lemniscate trajectories that can be computed, and it's all very interesting. Now, it's particularly interesting to me because in general relativity, two modes can never exactly cross each other. However, if I consider theories beyond general relativity, the simplest thing that I can consider is perturbations by a massive scalar field, where I introduce an additional parameter. Or I can take, for example, Kerr de Sitter. That's already beyond GR to me, okay? It's not really, but it's just GR with a cosmological constant. Then I can make these two modes cross each other exactly. So the case of a massive scalar field, let me show you, was done in this nice paper by Cavalcante and others. They also have follow-up papers. What they find is that if you consider perturbations induced by a massive scalar, then two modes can cross each other. And when they cross each other, you have hysteresis. So this means that as you go from one point in this case, black hole spin versus mass plane to another, what you get depends on the path that you trace in the scalar field mass versus spin plane. This is super interesting. I can tell you that we're finishing a paper where we do the same for Kerr de Sitter, and we study how this generically affects the spectrum in Kerr de Sitter. And the same thing happens. So in the presence of a cosmological constant or a massive scalar, the outcome of what you get, what you call the fundamental mode or the first overtone, depends on the path. And more interestingly, whenever two modes cross each other, the amplitude of the originally suppressed mode can become resonantly excited. So this can have very interesting implications if you want to look for theories beyond general relativity. And we described what happens analytically in a paper that we published in PRL, led by a Chinese student, He Shu Yan. I can go into a lot of detail, but again, I'm going to skip it because I ran out of time. And like I said, this is related to tests of theories beyond GR, which I will also completely skip. And I will leave you with a take-home messages slide, and I will take any questions. If you're interested in the part that I skipped, I can go back. If you're interested in anything else, please ask. I'm sorry for running over time.
Thank you, Emanuele, for a great talk.
Thanks, Shahar.
So more questions, please.
Thank you for the great talk. I wanted to ask about this last point. Why specifically new physics was sensitive to this effect?
So this is a whole story that it will take me a while to tell, but let me explain. If you go to theories beyond general relativity, for example, you consider Einstein scalar Gauss-Bonnet or dynamical Chern-Simons or other effective field theory modifications of GR, what you're going to get in general is that the additional modes will depend on the parameters epsilon1, epsilon2, epsilon3, say, of your effective field theory. You don't even need to include additional fields. Small add here. There will be a paper next week where we study how these additional terms break isospectrality and the relation between isospectrality breaking and the so-called Penrose limit, which I also did not discuss. But we think there is a very interesting connection between isospectrality breaking in modified theories of gravity and the symmetries of light ring physics. You will see. I think I'm very excited about this, but I didn't have time to talk about it today. So what happens in general is that if you want to compute the quasi-normal modes in these theories beyond GR, you can do it theory by theory. So you can introduce additional parameters, say epsilon1, epsilon2, epsilon3, you can compute, or lambda even, lambda odd, and you can compute the modes in these modified theories of gravity. In general, what do you find? Well, what you find is that you get some corrections to the original potentials that on a theory by theory basis will depend on some inverse power of 1 over r to leading order. So I got really excited about this initially because you can imagine that with this additional parameter, you may have subleading modes in the spectrum that would not be excited in general relativity, but when the parameters of your system, in this case, one of these alphas and the spin, are such that the modes are resonant, then the subdominant modes may be excited to detectable levels. We never published this, and the reason is that we looked into it and we found that these exceptional points can happen indeed, but they usually happen in a regime in which these alphas violate the smallness assumptions that are implicit in the effective field theory treatment. So this is possible, but in general, it's going to be hard. However, don't lose all hope because there is a paper that I mentioned at the bottom here by Takahashi, Motohashi, and Takahashi, where they took a very reasonable theory. They took Einstein-Maxwell axiom, and they show that in that case, you will not have exceptional points, but you can have avoided crossings of the fundamental modes that correspond to the gravitational, vector, and scalar degrees of freedom. And when you do, they observe a resonant excitation of the subdominant modes. Not quite a divergence, but a very large enhancement. So I think that this is very exciting, and yeah, we're looking into it, and I'm sure there will be more to say about it.
Thank you.
Mm-hmm. You're welcome.
More questions?
Yes. Can you say a bit more about the criticism of the 250114 interpretation?
Yes. So what I can say is this. I don't have slides on this, I think, but what I can say is that if you're often, I'm sure you were involved in the original analysis, and there is in the longer ring down paper. Sorry, someone is knocking on my door, I believe. Let me just. Yeah, sorry, Vishal Baiba, who led one of these papers, is visiting us today, and he was. So now you know that there is a material, I believe it's in the supplemental material, there is this plot of the amplitude of the overtone as a function of time, right? And the claim is that if you look at the amplitude of the overtone between about 5m and 10m, there is an unambiguous non-zero amplitude of the overtone. I personally find it convincing enough. I think that the non-zero amplitude of the overtone is there. What is still not completely convincing to me and Mark Chung in particular is whether the amplitude of this first overtone is constant enough and the frequency of the putative overtone that you are measuring is insensitive to the assumptions that you are making. So I am not involved in this, but I've been talking with Mark, who has been developing his own pipeline to do ring down extraction at the IAS. And he now has a tool that, like he always does, because he's amazing, he will probably make public, where you can change a lot of assumptions on things like how many modes do you include in the analysis, how early do you start the fit, and so on and so forth. And I'm not spilling any beans here, because he gave a talk at the APS on some of his preliminary results. And I can tell you, you can send an email to Mark and ask him if you want. But what he finds seems to be somewhat sensitive to assumptions that you make on the priors and on the starting time. And so, as usual, we're trying to be conservative and we're saying, yes, I really think we have detected a second overtone there, but the level of accuracy with which you can make these measurements really depends on the assumptions that you make. So we gotta be careful. That's all.
Okay.
I still believe personally that the best tests that we can make are if we see an asymmetric loud binary, because then we're going to observe fundamental modes for 2, 2, 3, 3, and we're done. And everybody is happy.
We'll get there. We'll get there.
We will, I'm sure.
Any more questions? Well, I wanted actually to ask again about the high spin limit, which you showed. So I wanted to understand better what you were saying about this. So is there a match with the analytic result, or you said there are different assumptions?
So yes, let me explain. Where am I going? I think I went too far. I wanted to go to, where is the slide? Here. Okay, so the formula that you see at the bottom, Shahar, is your formula. Now, we are trying to better understand your paper, and we are also responding to the referee of this paper these days. So what do we find? We find that the C that we plot there is actually not psi. It's the amplitude of the H, it's the actual strain, okay? Yeah. And what we find is that the amplitude of the strain seems to increase. And if you look at the zoom in close to the extreme limit, now we have better data because Laura has been extending this work to do all of the elements, where this is incremental and very painful and very tricky work. But okay, we're on it. So what we find is that the amplitude of this C grows when A over M goes to 1. In your paper, you have a prediction for the C and LMs, but as you know very well, what you do is something different. You take the near neck approximation, and then you take a particle that falls across from one of these critical geodesics, and you compute the radiation emitted in that limit. And the key factor in this equation is this factor over here, where I didn't copy all of the equations from your paper, but these are not, goes like 1 over kappa. So if I look at your prediction here, I have to say, we spent about an hour talking about this with Tony Riotto, who got also very interested in this topic. And so I thank him and Davide Perrone for reminding me that you had told me to read your paper, which I should have done when you told me. So what happens is that if you take this equation at face value, h is just a number. It's 1/2, I believe. But this would predict that for the fundamental mode, you get, I would say, a kappa, not a divergence, for sure. And then as n increases, because this guy goes like 1 over kappa, you would expect that the amplitude of each of the overtones would go like 1 over kappa to the n. So you would expect, as we observe, that for kappa equals 0, the amplitude vanishes. For n equals 0, the amplitude vanishes. For n equal 1, it diverges a little. For n equal 2, it diverges a little more, and so on. This is what I was saying. In the last few days, I can tell you, if you don't scoop us, that we try to check if this actually happens. We don't expect perfect agreement with your equation because you do a different calculation from what we do. We start from the actual ISCO, we perturb it a little bit, we let the particle drop, and we do the full integral. And then we need to renormalize it because, as you know, these integrals are divergent. It's a pain in the neck. But okay. Again,
Literally a pain in the neck.
I know. I was intentional again. I'm very good at dad jokes. But so then we try to fit the data here to check if the increased divergence that we observe is indeed an integer, and it's not. So I can tell you that I asked Laura just yesterday to do these fits, and she finds that yes, the exponent is changing. In a log-log plot, it's all linear, but the coefficient is not an integer. So I'm very interested in understanding what's going on here. How do these modes actually diverge for a realistic astrophysical source? Is it related to all of your network? How? I'd be very happy to talk to you about this.
Interesting.
Mm-hmm.
Okay, thanks. Any more questions? Okay, so if not, let's thank Emanuele again.
Thank you all.
Thank you.
Thank you. Thank you.